We are only going to derive the work energy theorem for the simplest possible case. We have a particle of mass m located at point A. It moves in a straight line to point B over a distance s. The resultant force on the particle is F. To keep things really simple, F is a constant force, and we will make it point in the same direction as the direction of motion of the particle. Let's consider the work done by F on the particle. Well, from previous videos we know that we have to get the component of the force in the direction of motion. Well, that's easy in this case, because the component of F in the direction of motion is F itself. It's the magnitude of F, which is just F without the arrow. We multiply that component by the distance s that the particle travels. Next, we use Newton's second law. F is the resultant force on this particle. And we know that the magnitude of the resultant force on any particle is the mass of the particle times the magnitude of its acceleration. F equals ma. Now, suppose that the initial speed of the particle is u. Of course, we know the direction of u, it's pointing to the right. Suppose that the final speed of the particle is v. Now, since the resultant force acting on the particle is constant, it means that the acceleration of the particle is constant. See, that's just by F equals ma. If this vector, the resultant force, is constant, then the acceleration vector is constant. So, if the acceleration vector is constant, it means that its direction and magnitude is constant. Its direction is in the same direction as the resultant force, and its magnitude is constant. And we know how to connect final speed, initial speed, and distance if the acceleration is constant. So we're dealing with uniform linear motion here. So we can use this formula. So we are going to replace A with v squared minus u squared over 2s. So just subtract u squared from both sides of this linear motion equation and divide both sides by 2s. Okay, if we do that, you can see that the s's cancel, and if we multiply in by m over 2, or a half m, we end up getting a half mv squared minus a half mu squared. Now, a half mv squared is called the kinetic energy of the particle. Actually, in this case, it's the final kinetic energy of the particle. It's the kinetic energy of the particle when it reaches point B. You can see that the kinetic energy is proportional to the mass. I'll just write K for kinetic energy. K is proportional to m. So if we double the mass of a particle, we double its kinetic energy. We can also see that K is proportional to the square of the speed. Now, so the kinetic energy goes up much more quickly when the speed is increased than when the mass is increased. So you can see that if we double the speed, the kinetic energy goes up by a factor of 4. If we triple the speed, the kinetic energy goes up by a factor of 9. So that's why in the case of a car crash, if a car crashes at 50 kilometers per hour, the energy that goes into the crash is only quarter what it would be if the car crashed at twice the speed, say at 100 kilometers per hour. Now here we have the final kinetic energy of the particle minus the initial kinetic energy of the particle. That's the change in the kinetic energy, or delta K. Well, we could say the difference of the kinetic energy. Now, we know that work is measured in joules. It's also a scalar quantity. It doesn't have any direction. V is the speed of the particle, not the velocity. So the direction of the speed is immaterial, actually, in the general case. Similarly, u is just the speed. It's a scalar. So, you know, we have that work is a scalar quantity. We know that its unit is the joule. Force multiplied by distance, Newton meter. So the unit of kinetic energy is the joule. Kinetic energy is often referred to as the energy of motion of a particle. Now that makes sense, because if the particle is motionless, if it's at rest, then V is 0. And of course, if V is 0, the kinetic energy is going to be a half times m times 0, which is 0. So a particle has no energy of motion if it's... Now, as an aside, I'll just discuss the general case, which I think is worth mentioning. The particle starts out here at point A, its mass is m, and it follows this curved path. F is the resultant force acting on the particle. Now F can vary, it doesn't have to point in the same direction. So for example, when the particle gets to here, F could be in the direction shown. When a vector varies, it can vary both in direction and magnitude. So that's what could happen. Now, to calculate the work done by the resultant force over this path involves methods that are beyond this course. For anyone that's interested, I'll briefly mention the approach that has to be taken. What we need to do is get the work done by the force over tiny increments of the path's length. So let's suppose the particle gets to here, and the distance travelled is ds. So we would have to get the work done by F over this tiny increment ds. That would involve getting the component of F in this direction, in the direction of the increment ds, multiplying that component by ds, and we'd have to repeat that for all such increments. So you know, okay, the particle moves another tiny distance ds. See, ds is in a different direction now. We'd have to consider the work done by the force as the particle moves from here to here. So the force at this position could be different from here, because the force could be varying. The force might look like this, you know, and we can imagine summing all the works done over these tiny increments from point A to point B. So this is an integration problem. Now fortunately, with the work energy theorem, the work done by the resultant force over this path A to B can be calculated by just knowing the initial and final speeds of the particle. We also need the mass of the particle, of course. So here's the initial velocity vector. Now the direction of this vector doesn't matter. All that matters is its magnitude. That's the speed of the particle. And we need to know the final speed, so the direction of the final velocity vector doesn't matter. It's the magnitude that matters.